In this next section, we'll be going through the wires, basically what connects the different logic stages together. So first I'll do a brief introduction about wires. Then we'll go into interconnect modeling, which is we have resistance of wires and capacitance of wires, talking about how that RC, resistance and capacitance, causes delay through your wires. Next, talking about what's called crosstalk. That is when wires are routed next to each other and one is switching or both are switching, that they will basically have some capacitance to each other and they will have some effect on each other. As one is switching, it will induce noise on its neighbor. So then we'll talk about how we can engineer the wires to try and minimize some of the bad effects of RC and crosstalk, etc., and how we can use repeaters to also try to minimize some of these effects, trying to minimize delay and trying to get rid of noise or reduce the effect of noise using repeaters. So as an introduction, up until now, a lot of what we've been concentrating on is how you build transistors, use the transistors to create logic gates, and then hook them together. And so we spent a lot of time on the transistors and logic gates. In reality, when you think about it, IC chips are really mostly made up of wires called interconnect. And because the wires that we have in modern microprocessors, you might have 10, 12, or more actual layers of wires, whereas you only have one layer of transistors. So in reality, you really do, your interconnect is making up most of the processing, the process technology creating your IC chip is a lot of steps of interconnect, and your actual mask layers are a lot of steps of interconnect. So they're really a major part of your design. So when you're looking at your stick diagram, the actual connections between your transistors and the wires of those connections a lot of times can determine the size that your cell is going to take up. And so in reality, the wires can make up the size and the area that you're consuming as much, if not more, than the transistors, depending on the situation that you're in. And like I said, there's many layers of wires. There's only one transistor layer. So in effect, your wires really are as important as your transistors in speed and power consumption, and also wires will introduce noise that you have to account for and try to make sure you introduce as little noise as possible. As I mentioned previously when we were talking about process technology, the wires tend to alternate, so alternating layers run at 90 degrees to each other. So your metal 2 might wind up running horizontally, and your metal 3 runs vertically, metal 4 again horizontally, metal 5 vertically, and by alternating what direction each layer runs, you can wind up not having, you can make the best use of your metal in order to get signals to the areas that you need to go. So first let's discuss our wire geometry, some figures of merit, or at least figures of merit for your wires are, one of them is pitch. That is what's the distance from one wire starting to the next wire starting. So that would be the width of your wire plus the space to the next wire. So your pitch is the width plus your space, and so that's how much a given wire needs to take up before you can get to the next wire. Then you also have the aspect ratio of a wire, which is the thickness of the metal divided by the width of the metal. So the aspect ratio, the thicker your metal is, the higher it is relative to the width of it. So in older processes, the aspect ratio was much, much less than 1, which meant that your metals were in general a lot wider than they were tall. But in modern processes, the aspect ratio has gotten much taller, so you can get wires a lot taller and closer together, so you can get more wires spaced next to each other over a given unit area, but they're very, very tall wires. So you're packing in a lot of wires close together that are really skinny relative to how tall they are. And we'll go into how that affects your wire properties. So another thing to know about metal, in addition to your pitch and width and height, is where you are in the layer stack, because where you are in the layer stack will actually help determine what the minimum width and thickness and etc. and properties of your metal. So for just historical notation, in a 0.6 micron process many years ago from AMI, the process only had 3 metal layers. Metal 1 was used for just within the cells routing, metal 2 vertical routing, and metal 3 horizontal routing. So not too many metal layers, and there's only so much that you can do with a limited number of metal layers. Whereas in modern processes today, what's listed here is 6 to 10 plus metal layers. That was back several years ago, actually. In current modern processes, there's probably more like a minimum of 9 to 10 metal layers and going up to 13 plus metal layers in current modern processes. So typically the lowest level metal, like your metal 0 or metal 1, are very thin, very narrow, near your 3 lambda width for your process technology. Tends to be pretty high density so that you can use it within the standard cells and get as many wires as possible, connecting up internal to the standard cells or to neighboring standard cells. Your mid-level layers will be a little bit thicker, a little bit wider, in order to try and balance maybe a little bit less density, but more speed, less resistance, and a little bit wider space between metals to get a little bit less capacitance as well. And then when you get to the very top layers, they'll be really thick, really wide space, and your most top layers will be used mostly for your power, your ground, and your clock distribution, where you need as low a resistance as possible. Here are a couple examples, and these of course are fairly old examples of Intel 90 nanometer stack where there was 6 metal layers, and you can see the lowest metal layer is can be the narrowest with narrowest spaces. As you go from metal 1 up to metal 6, you can see the width of the minimum width metal 6 is much wider than the minimum width metal 1 by probably a factor of 4 or 5. Kind of hard to tell exactly here. But then going to the 45 nanometer where they went up to 8 metal layers, you can see the minimum metal 8 is definitely a lot wider than the minimum metal 1 down at the bottom. So with each process generation, usually there tends to be, not necessarily from one process generation to the next, you don't always get more metals, but between probably any 2 process generations, you almost certainly get like an additional 2 metal layers as we've been going on. Currently, we're around the 10 nanometer area, and like I said, up in the 12 plus metal layers is typical for 10 nanometer, and going on to 7 nanometer, depending on which foundry you're going to, might even go beyond 12 or 14 metal layers in the near future. So talking a little bit about how do you model, how we model our interconnect in an IC device. We can think of current in a wire as being somewhat analogous to current of water flowing through a pipe, where the resistance is related to the size of the wire or the size of the pipe. A narrower size will impede flow. So like if you think about a water pipe, a certain size pipe, no matter how much pressure you put the water under, there's a certain maximum flow that runs through it. So the resistance is somewhat like that. Capacitance of the wire could be thought of similar to if you had a trowel under a leaky pipe. If you're trying to flow water through the pipe, you need to first fill the trowel and then you start getting water flow through the pipe. And inductance can be thought of a little bit like a paddle wheel, where once you get the wheel going at a certain rate of flow, it doesn't want to go at a different rate. So both going faster or slower, it's going to kind of resist changing the rate of the flow. Now, for most wires in an integrated circuit that are internal to your design, inductance is pretty usually ignored for virtually all wires. Some exceptions would include for I/O, things that are going off chip, so signals that you're sending off chip, and also your power network. So VCC and VSS tend to have some inductance that winds up getting modeled, but a lot of most of your wires internal to your design, you pretty much ignore inductance for internal wiring. So as I said in the previous foil, usually we ignore inductance, and so wires are generally modeled as just an RC system, so resistance and capacitance. There's a certain resistance per unit length and a certain capacitance to neighboring wires per unit length. And so if we really wanted to model it 100% accurately, we would break it up into a lot of really small segments, n number of segments that are a certain unit length, whether it's 1 micron or 1/10 of a micron or whatever you would want to call it. But that gets really, really complicated to, simulate a wire that has, 1,000 segments. Would take a lot of simulators, a lot more time. So typically we try to make a more simplified model, and a couple possible examples of simplified models would be using either an L model, where you have an R in series with a capacitor at the end, or a pi model, where you have half of your capacitance per unit length on either side of a resistance, or a T model, where you have half of your resistance on either side of a lumped capacitance in the middle. Turns out that using the 3-segment pi model is actually pretty accurate in simulation to using a bunch of individual smaller n number of segments. So it can be accurate to about 3% in simulation, whereas the L model needs like 100 segments to get the same accuracy. So typically we wind up using a single pi model for our Elmore delay and get reasonable enough accuracy doing that. So you'll see that most often and that's what I've always used when I've done RC pi models, RC delay for my simulations at Intel as well. So first let's go through how we calculate wire resistance. And the first thing to note is depending on the metal you have a certain resistivity to a particular metal that is formed as your metal layer on your IC circuit. And that resistivity is in ohms meters. So that is a property of what metal is being used and how you actually put it on your integrated circuit. So the value of resistance that you get is your resistivity divided by the thickness of your metal times the length of the wire divided by the width of the wire. And one of the things that's often done, because the thickness of your metal for a given metal layer is predetermined by the process technology you're using. So you can't, for a given wire that you draw in a given metal layer, you can't say, I want this wire to be thicker in metal 3 than a different wire that's in metal 3. All metal 3 wires are going to be the same thickness based on your process layer, process technology. So the resistivity of your metal divided by the thickness of the metal for a given metal layer is a new term that we're calling the sheet resistance for that particular metal layer. So all of your metal 3 wires, for example, will have the same thick sheet resistance, which is given in ohms per square. And square is basically a dimensionless unit. So our sheet resistance is ohms, but ohms per square, and then we need to count the number of squares to determine the total resistance of that wire. And the squares is the length of your metal wire divided by the width. So that's the definition of the total number of squares of your wire. So a given wire that is a length of L and a width of W will be the same number of squares that a wire that's twice the length and twice the width of that wire. It's just a function of the total L divided by the total W for a given wire that you've drawn out. So you can basically get the resistance of a given drawn wire by taking your ohms per square, which is a function of a particular metal layer in a particular process technology, times the number of squares, which is length divided by width. So as I was talking about last week, as far as metals that we can use in integrated circuit technology, up until approximately the 180 nanometer generation, most wires were made of aluminum. It's a pretty good metal as far as resistance goes. But in the latest process technologies, because of the Damascene process, we normally use copper now because we now have a way of protecting the silicon from the copper, where copper wants to diffuse into silicon and it would damage our FETs and damage our oxides. But we have a way to put a diffusion barrier in place now, process technology. And so copper, if you look at below, the bulk resistivity in micro ohm per centimeter, given below, aluminum is 2.8, whereas copper is 1.7. So it's actually lower resistance than aluminum, and so we get better effects of lower resistance using copper in modern process technology. The other thing to keep in mind with our resistance of our wires is not just the length of the wire itself, we have to make contact between our metal 1 wire or metal 0 down to our actual active transistor region. And each contact has a set amount of resistance to the contact itself. or if we're going between a metal and the transistor, we call that contacts. If we're going between metal and another metal layer, we call that vias. So these contacts and vias have their own amount of resistance per contact or via. So if you make a single contact down to your active region or between metal regions, you might have, for example, 2 ohms, or as you go to the lower metal regions, the smaller the contact or V is, the larger the resistance is. So you might have up to 20 ohms, depending on which layer it is. So if you really want to lower your resistance, instead of putting a single contact to your active or a single via between, let's say, a metal 4 wire and a metal 5 wire, you might want to make a bigger area and place an array of contacts. Like, for example, shown below, there's 2 different examples here. One where they have a 2x4 array of contacts, and the other where it's a 4x4 array. So if you had a single contact, you might have 20 ohms. If you have a 4x4 array of 16 contacts in parallel, those now would take that amount of resistance and divide it by a factor of 16. And so you might go from 20 ohms down to effective resistance of 1.2 ohms or so. So using more contacts or more vias in parallel with each other will lower your resistance, and in some cases your contact or via resistance might be as much or more than your wire resistance if you have a wire that's not very long, for example. So always keep track of contacts and vias can be a significant issue on certain types of nets in certain situations. Now, one of the issues that I did not mention last week when I was talking about process technology is when you're using copper as a metal wire and you're using the Damascene process, we have this barrier between the copper and the silicon that's a different metal type. And the thing to keep in mind, I didn't mention then, is this diffusion barrier actually takes up some of your width of your copper wire, and it has a much higher resistance than copper. And so your effective resistance of your copper wire isn't just the total width of this metal wire, because keep in mind the width of the copper is reduced from the total width of the metal wire because there's this additional barrier there. So the effective resistance is going to increase because your effective width of the copper is less than the total width of the wire. And so you do get an increase to your copper wire resistivity because of that. And in addition, copper tends to be prone a little bit to dishing. When you're going through the chemical mechanical polish, you can get the very top edge of the copper wire isn't completely flat. It might wind up having a little bit of a dip in the top, and so you lose a little bit of your thickness, the height of your thickness. So you lose some of the thickness due to dishing, some of the thickness due to the thickness of the barrier on the bottom of the wire, and then you lose some of your width on either side due to 2x the barrier thickness on each side of the wire. So that goes into the total resistance of your copper wire as well. So let's go through a relatively simple example of computing resistance for a copper wire. So first, we want to compute the sheet resistance of, we have a copper wire that is 0.22 microns thick copper wire in a 65 nanometer process. And the resistivity of thin film copper is 2.2 times 10 to the minus 8 ohm meters. Now, if we ignore dishing, such that the thickness is the same thickness across the entire top of the copper wire, then we can calculate the resistivity in ohms per square as the resistivity of the thin film, which is the 2.2 times 10 to the minus 8 ohm meters, divided by the thickness in meters of the copper wire. So the thickness in meters is 0.22 times 10 to the minus 6, because it's 0.22 micrometers thick. So take the 2.2 times 10 to the minus 8 divided by 0.22 times 10 to the minus 6, and we get a resistivity, sheet resistance of 0.1 ohms per square. Now if we want to take that and calculate the total resistance of a wire, if the wire is 2x the process technology, I said it was 65 nanometer, so 2x that is 0.125 micrometers. So we have a wire that's 0.125 microns wide and 1 millimeter long. And if we ignore the barrier layer, as we mentioned in the previous foil, there would be some thickness and some width being taken away from the copper wire due to the barrier layer. But if we ignore that and calculate the resistance for this wire, we have 0.1 ohms per square times the number of squares is 1,000 microns, or 1 millimeter, divided by, that's the length, divided by the width of 0.125 micrometers, and we get a total resistance for this wire would be 800 ohms. Now, as we've said before, in addition to resistance of the wire, we also have wire capacitance. So wire has a given capacitance per unit length, which will depend on what layer of metal we're in as well. Because the capacitance, you have capacitance to your neighbors. So here below we're showing a wire. Assume this wire kind of comes out at you or goes into the screen. So we're seeing a cross section of this wire, and so we can see its width and thickness, but we can't see its length. The length is going into the screen. So we have capacitance in all four directions. We have capacitance to the layer above it, C top. We have capacitance to the layer below it, C bot. Those capacitances will likely be different from each other because it depends on the thickness of the oxide layer between layers. So between layer N and layer N plus 1, there will be a thickness of oxide that is H sub 2. And between layer N and layer N minus 1, there will be a potentially different oxide thickness of H sub 1. So C top and C bottom are likely to be different from each other, whereas the width to you also have capacitance to your neighbors. So the width of the wire adjacent to you on the right and the left, the minimum width or minimum space that you're allowed in a given metal layer will be the same on either side. So you have the maximum capacitance that you can have is C adjacent 2 times that, one for on the left and one on the right of the wire that you're driving. Just a couple things to note about capacitance. If we go back and just review parallel plate equation for capacitance is equal to the epsilon oxide, whatever your oxide constant is, times the area of the plate divided by the distance between one plate and another plate. So while wires are not parallel plates, they do obey the general trend of that equation, which is if we increase the area of the wire, it will increase in capacitance. So Increasing area can be done by increasing the width of the wire, which you do control for a given process technology, or increasing the thickness of the wire, which you don't control. Once you choose a given process technology, a given wire thickness for a given layer, if you make the wire thicker, it will have more capacitance to its neighbor next to it. It won't have more capacitance to the layer above it or below it, but more capacitance to its neighbor. But the distance of the wire to the left or right of it is the space. So increasing the distance to the wire to the left or right, if you increase your space, you can decrease your capacitance. And if you choose a higher level metal that has a larger distance or more oxide thickness between so when you get to the higher level metals, the one metal layer to the next metal layer will have a larger oxide thickness between metal layers, which is the H value. So higher level metals tend to have lower capacitance to the layer of metal above them and the layer of metal below them because they have a thicker oxide between metal layers. And of course, your dielectric constant for silicon dioxide, the value of K goes into your epsilon oxide is K times epsilon 0, which is a constant, and your K for silicon dioxide is 3.9. In modern process technologies, as I went through last week, they're starting to use lower K dielectrics, below 3 or even lower, and in order to try and reduce capacitance as much as possible. So just quick note here about giving you an idea of capacitance ratios. For like M2, metal 2, typically if you have dense wires in metal 2, you might have a capacitance for at least the process technology we're talking about here of approximately 0.2 femtofarads per micron unit area, which can compare, if you're looking at gate capacitance in this same process, to 1 to 2 femtofarads per micron for gate capacitance. So just to give you an idea of comparison, your metal 2 wire capacitance might be approximately 1/10 the value per unit micron of what your gate capacitance is. So it just gives you an idea of how metal capacitance compares to gate capacitance. It might sound like it's a lot less, but your wires tend to be a lot longer than your gate size is, and so you can see where you could wind up having your metal wires add up to the same amount or even more than what your gate cap is, depending on how many things. If you have a large fan out, you're going to have much more metal, and that metal could wind up adding to as much capacitance as your gate caps of your fan out is. So wire can have a significant effect on your overall load that you have to drive. Now, in addition to your metal wires, your diffusion areas of your transistors and your polysilicon of your transistors also have resistance and capacitance to them. So some notes about those values. For diffusion, your capacitance is actually pretty high because of the reverse bias p-n junctions that you can have there, which can be 1 to 2 femtofarad per micron. So it's comparable to your gate capacitance. And in addition to that, your diffusion also has a high resistance. So you have a high capacitance and a high resistance to diffusion. And for that reason, you should pretty much always try to avoid using diffusion as a wire or a connection layer. It really doesn't work well using diffusion as a connection layer. Although a lot of times the tools that you run will treat it as if it's a normal connection, and so it can confuse and potentially cause problems because the extraction tools will extract it as if it's an actual connection logically, but it acts like a really, really bad connection in the physical world. And so you might see a failure even though logically everything looks like it should wind up working. Now polysilicon, on the other hand, has a much lower capacitance than diffusion does, but it has a fairly high resistance. So typically it's only used for transistor gates, and occasionally you'll see designers use it to connect up, make connections as very short connections between gates, but be very careful to try to make that as short as possible. In the latest process technologies, there tend to be more rules around just how long you can make those and what types of connections you can use. In older process technologies, it used to be used a lot more often to make connections between gates, and even have sometimes longer than they should have been connections between gates. So you don't see that as much in the most recent process technologies, though. So let's go through an example of if we have a inverter driving along a long wire to a receiver. So in this case, we're going to try and estimate the delay. We're not trying to get an exact number, but an estimate of the delay. If we have a 10x inverter driving a only 2x inverter, but it's at the end of a really long 1 millimeter long wire. Now assume that the capacitance of the wire is a unit capacitance of 0.2 femtofarads per micron, and that if we had a unit sized inverter or minimum sized inverter, it would have an equivalent resistance of 10 kilo ohm and a input capacitance of 0.1 femtofarad, or capacitance per unit of 0.1 femtofarad. So in this case, our driver is a 10x driver. So on the left side we see it has 1/10 the resistance of a unit inverter. So instead of 10 kilo ohms, we have 1 kilo ohm, or 1,000 ohms. That is driving a wire that we're modeling as a pi model. That wire, since it has a unit capacitance of 0.2 femtofarad per micron, and it's 1,000 microns long, or 1 millimeter, it has 200 femtofarads total capacitance. We'll take 100 femtofarads on either side of the full resistance of that wire, of 800 ohms. And so we have 100 ohms on either side of the 800 ohms for the wire. And then the receiving inverter, keep in mind, is 3 units because the P is size 2, N is size 1. So a unit size inverter would be 3 units. The units are each 0.1. We're 2x that size, so we're 6 units. So we have 0.6 femtofarads load at the end. So if we try to estimate the delay there, we can use RC time constants to estimate the delay. The first estimate would be our driver of 1,000 ohms driving that first 100 femtofarads. So the RC there is 1,000 ohms times 100 femtofarads. The second set of RC that we would figure out would be 1,000 ohms plus 800 ohms driving the capacitance on the right side of the 800 ohms, which is 100 femtofarads plus 0.6, so 100.6 femtofarads. The overall amount of propagation delay there is 281 picoseconds. You can see if we didn't have that long wire there, and we just had the driver driving the load and figured out the RC time constant for that, it would come out to just 0.6 picoseconds. So obviously 99.9% of our delay here is exclusively due to the long metal wire that's in this. So wire delays can have a very dominant effect if you have very long wires, much more so than just the load load gate that you have on a given driver. Now, in addition to delay, wires will also require power, even though they're a passive element, not an active element. The fact that wires have capacitance to them requires some amount of energy to charge them and energy to discharge them. So let's go through an example of if we want to estimate the energy per unit length to send 1 bit of information along a wire. That means charging it and discharging it. So a full charge and discharge cycle. How much energy does that require? Let's assume a wire cap the same as we just went through in the previous example of 0.2 femtofarad per micron. So if we do that calculation, 0.2 femtofarad per micron is equal to 0.2 picofarad per millimeter. If we assume in a lot of modern process technology right now, 1 volt is a good voltage that is often used still in current process technology. So if we take the capacitance times CV squared, will give us the energy consumed. So that will equal 0.2 picojoules per bit per millimeter. And then if we have that running at 1 gigahertz or 1 gigabit per second, that will require 0.2 milliwatts per millimeter at 1 gigahertz. And so you can see that, if we have a millimeter long wire, 0.2 milliwatts doesn't maybe sound like a lot, but keep in mind that there's tens of thousands, if not hundreds of thousands of wires in your design, and so that can add up to multiple watts if you're toggling all your wires in your design at a gigahertz clock speed. So your wires do definitely add up in terms of power as well as delay, and so it is something that you definitely need to account for and measure as you're trying to determine your performance and power and speed of your circuit and your design.